Alright, so today we're going to be talking about the laser pointer in more details. So the laser pointer's fully disassembled looks more or less like this. It has a laser that has a TO-CAN package right here, and the TO-CAN package is directly soldered onto a printed circuit board right here. This printed circuit board, this PCB, has its wiring desoldered, so for illustration purpose. And the can, it's a TO18 5.6 millimeter can. It's a commercial standard, and the can is pressed into a laser holder. So this can right here has it's press fit, just press fit into the laser holder right here on the back end of the laser holder. And the laser holder has a male thread that engages to the female thread on the enclosure, and also a female thread that engages to the lens holder, which houses the focus lens. The focus lens sits somewhere in here. It's around 6.3 or 7 millimeter diameter. And the thread pitch on the lens holder is around it's actually 0.5 millimeter. So every time you rotate full revolution of the focus lens holder, the focus is going to be in to the laser or out of the laser, get closer or further away from the laser by 0.5 millimeters. And furthermore, there's a linearly knurled cap that allows you to adjust the lens holder easily. So usually the lens holder and the caps are glued shut together or threaded really tight. So as you turn the cap, the lens holder turns with it. And in between the lens holder and the laser holder right here, there's a backlash spring, so that takes out any backlash of the male thread and of the lens holder and the female thread of the laser holder. So that allows you to have a better focus adjustment. And depends on the availability of the laser. Sometimes the lens holder is made out of brass, and sometimes the lens holder is made out of plastic. So what we're going to talk about next is we're going to go into more details than on the electronics that's driving the laser itself. So this is how we reverse engineer the circuit. So the circuit diagram is not available online. At least I couldn't find it. So what we have to do is we have to figure out what the circuit looks like. So this is what we did. The first step is to take a close-up picture of the circuit with your cell phone. So there's two-sided circuit board, so you could sort of see these pins are coming off the laser can. On the front side, that's called the side A, and then the other side, when you flip it over the board, the printed circuit board, is side B. And the next step is what we do is we desolder every component with a hot air gun. So you put some hot air to melt the solder, you remove the wiring, and you remove every single component. And then you get another set of image that have all the components on the printed circuit board PCB removed. So, and the reason you do that is then you could see the traces really clearly. So you could see which components connected to where and how. So say for example on the bottom corner of the side B, where my mouse point is, you could see that there's a black wire connect to this node, and therefore the leg of this component and the leg of this component and the leg of this component, it's all shorted together and they're all grounds. So this node on the circuit is ground. So to trace out the circuit, what we need to do next is to turn the picture black and white into grayscale. And the reason you do it this way, turn the picture in grayscale, is so to label the components with some colors. It's just for convenience. You don't have to do this, but this makes your life a little bit easier. And then the other thing we did is we flipped side A vertically, so that way the V plus is on the same side as the side B. So what we did is we label every single node So this red wire comes in, we call it V+, and we reference to the same board that has a component removed V+ right here as well. And over here we could find out what type of transistor it is by looking the number IF. So right here you see the laser engraving on the SOT23 package. This is an IF. So if you Google IF with SOT23, SOT23, you know this is an NPN transistor of a certain family of certain kind, certain part number. And from that you look up the spec sheet and then you can find out the pinouts for that transistor. So this is a base, this is an emitter, this is a collector. And the other thing we do is we give each component on the circuit a designator. So this would be Q1, R1, Q2, R3, R2, and so on and so forth. So there's not a particular rule for giving a designator. We just want to call them uniquely. So when we draw the circuit schematic, we know who is who on the schematic. And the next step is to, once you have the designator in orange, then you label each of the pins of each of the components, each of the designators. And then the last thing you do also is to put some designator for the package of the laser itself. So you could see there's two pin 1 and pin 2 is on this side of on side A of the board, and pin 3 is on the side B of the board right here. So now we have every single pin of every single component all labeled. Then the next step is to draw the circuit, and this is the circuit that we came up with right here on the left hand side of the slide. So you could see that these it's a very interesting circuit, and at the time of I reverse engineer the circuit, I still didn't know what the package of the laser looks like, but it sort of makes pretty obvious sense that P2 and P1 has to be the laser anode and cathode, and photodiode anode and cathode. What surprises me is this circuit is actually a constant intensity circuit. So the way this works is that the laser is obviously powered up by the 3-volt rail. However, the current going through the laser, it's actually controlled by Q1, so controlled by this transistor, which is a BCB47B transistor. It's in SOT23 package, like what we saw. And over here, the transistor, this Q1 transistor, is further controlled by a voltage divider circuit. You could treat this as a voltage divider. So the bias on the base of the Q1 is controlled by wherever this voltage is at this junction. And this voltage right here, the controlling voltage of the current that going through Q1, and the voltage is controlled by these reverse biased photodiode here. So as the light shines onto the photodiode, the photocurrent generated is being converted to a voltage through the R3, and what that does is then the voltage produced across R3 will be used to bias Q2, and this is how the intensity of the laser diode could be monitored through the photodiode, and you could couple the photodiode and the laser diode together to achieve constant intensity control. Pretty common scheme in controlling the laser diode to be constant intensity. However, it's really surprised to see it on an inexpensive laser pointer in this case. But nevertheless, this is how the circuit looks like, and the whole circuit is powered up by two AAA batteries, right? So the two AAA batteries, the other thing we measure on the circuit is the amount of current draw we have. So on the battery terminal, if we give it a 3 volt or roughly 3 volt supply, then the measured current draw of the circuit is around 12.3 milliamps, and if we measure the voltage across the shunt resistor here, R2, the current draw is around 11.5. So the difference between what you supply at the rail and the current that's flowing through this Q1 transistor, it's very close to each other. So only 1 milliamp of circuit is used right here to the monitoring portion or a controlling portion of the circuit, and most of the current is going through the Q1, which is the driving part of the laser diode circuit. So this is a very efficient circuit to be used for a laser pointer, which is intended to be battery operated. And this may not be the correct data sheet, but this is the closest I could find that probably fits the description of this laser pointer. So as you could see, if we trust this spec sheet, this is a pinout in the spec sheet, and it matches the pinout that we expected to be from reverse engineering the circuit. And the laser wavelength is 650 nominal, and threshold current is around 15, which is a little bit surprisingly higher than the one we measured, which is only around 10 or 11 milliamp. So that's why I was suspecting that the laser that's actually in the package may not be the same as the one on this assumed to be a spec sheet or a data sheet. And the operating voltage is around 2.2 volts. So if you look at here on our circuit, on the collector side of the transistor Q1 leg 2, this measure voltage it's around 0.97 volt, say call it 1 volt. So the voltage drop across the laser diode is around 2. So it sounds about right, but it seems like the actual laser we have in the laser pointer is a little bit more efficient than this one here in the data sheet. So now a few things about these transistors. So when you look up the transistor, the easiest way you could look them up is just Google the laser inscription mark on, or laser mark on the transistor package itself. So if you type in 1F SOT23 in Google, what you're gonna get is you're gonna get a spec sheet that looks like this, and the spec sheet that looks like this. So so this is the two transistors that's used on the circuit itself, and it's a very common transistor. So this is NPN, both of them are NPN transistors. This is NPN 3904. This has been around for many years, probably 20-30 years at least, and same as BCA47. So this is the complete circuit of the laser printed circuit board. And also there's a decoupling cap. I didn't bother to measure the capacitor values, but it's just to stabilize the voltage and decoupling the any noise coming in from the power supply. So this concludes the more detailed discussion on the laser pointer itself, and then in the future video we might be able to open up the can and look at what's inside the can of the laser diode under a microscope and find out more about this the lasers inside the laser pointer. So thank you very much. See you in the next video.